Okay, into the final subtopic of the year, and this is nuclear fission and fusion. And in this first part, we are going to focus mainly on nuclear fission. So, why are these things important? Well, nuclear fission is the process which nuclear power plants use to produce energy. A byproduct of nuclear fission is the generation of neutrons, which is used to make a lot of medical radioisotopes. And nuclear fusion is the process that happens in our sun and in all stars for that matter, that allows them to produce large amounts of energy. And in a sense, it is also the holy grail in terms of where we would like to get to in terms of energy production on Earth, because it has the potential to provide basically limitless amounts of energy with minimal emissions or dangers, and it is essentially renewable, but we're probably still a long way off that at the moment. Okay, let's get into it. So what is nuclear fission? Well, nuclear fission is the process in which a heavy nucleus splits into two lighter nuclei. Now, some heavy nuclei undergo fission spontaneously, so it just happens. We briefly talked about that when we talked about the types of radioactive decay. One of the ways that heavy elements can decay is through spontaneous fission, but we don't need to know a lot of detail about that. What we're more interested in is this. Fission can also be induced in some heavy nuclei by the capture of a neutron. In either case, the nucleus splits into two nuclei and several neutrons with accompanying emissions of gamma rays. So, what happens in induced fission, which is what we're most interested in, is we have an isotope, one normally that will, not every isotope will undergo induced fission, but we have uranium-235 here that will. We fire a neutron into that. As that neutron gets absorbed, it sets up this unstable nucleus. We get this sort of elongated shape, and then you can think, as we sort of stretch this out, the electrostatic repulsion takes over and becomes stronger than the strong nuclear force that holds the nucleus together, and that leads to it splitting into two smaller nuclei. These nuclei that formed are, in a sense, random, in that you don't always get the same two form, but you tend to get two that are generally roughly half the mass of the original one. Only roughly half, you can see they're a fair way off half, but generally two similar sized isotopes are produced. These are obviously produced in an excited state, so there's the release of a lot of energy through gamma radiation as they relax, and also we get about 2 to 3 neutrons released in this process. Now, these 2 to 3 neutrons are going to become important because with a couple of little fine-tuning things, they can hit more isotopes and cause more induced fission. We'll talk about that in the next slide. Now, the total mass of reactants in a fission reaction is greater than the products, releasing energy given by E equals delta mc squared, where delta m is the mass of the reactants minus the mass of the products. So we have a mass defect here. That mass is converted into energy, just like what we looked at in the structure of the nucleus topic, this idea that energy can be converted to mass. This energy is released in the form of the kinetic energy of the product particles and the energy of the gamma ray photons that are released. Important here to note, this is I think for the second thing that we need to know, you get much more energy from nuclear fission than you do get from, say, a chemical reaction. If you want to compare, a chemical reaction will typically release electron volts worth of energy, where a nuclear fission process will induce mega electron volts of energy. So you're talking about, 1 million more times energy than you would get from a chemical reaction like burning a fuel or using a battery or something like that. So finally, I think I've covered this. Give a simple explanation of fission in terms of short-range nuclear attractive forces and long-range coulombic repulsive forces. So that's the idea, as this thing sort of changes shape when it absorbs a neutron, that the two sides get so far apart that the electrostatic repulsive forces take over from the short-range nuclear attractive forces. Okay, let's continue looking at this process and look at the chain reaction in the next slide.
Okay, so let's get into the chain reaction. There's a lot on this slide, but hopefully if you follow it through, it all makes sense. So on average, more than one neutron is emitted in nuclear fission. This leads to the possibility that these neutrons will induce further fissions, resulting in a chain reaction. So one neutron comes on, splits an atom, we get 2 or 3 neutrons released. Each of them hits another atom. They all split, release 2 or 3 neutrons. They hit an atom, they split. And before you know it, this one little neutron here has caused lots and lots and lots of atoms to split, huge amounts of energy to be released, and you have, if you like, a nuclear explosion on your hands, releasing large amounts of energy. However, if you're tempted to go out and make a nuclear bomb, it's not quite that simple, and let's explain why and how. So firstly, these neutrons that are emitted with very high speeds corresponding to 1 to 2 mega electron volts of energy. So 1 to 2 mega electron volts of energy. However, if these neutrons are to cause a induced fission, so split another energy apart, they need to get slowed down to about 10 electron volts of energy. If they have more than that, they tend to just either bounce off the atom. So it comes down to this sort of point here mainly. If they have too much energy, they will just either be absorbed and form a new isotope, or they will just bounce off the nuclei that they hit without causing any major change in its shape, and that setting up that instability that undercauses fission to occur. So, how do we slow them down? So to slow down our neutrons, we need to add a moderator. So a moderator is is something that we add to this system that the neutrons can collide with. In colliding with those, they can lose energy. Now, it's important though that this moderator have particles or atoms of a similar mass to a neutron, because what we know from conservation of momentum is that if these neutrons collide with a large atom, that they will bounce off with very little loss of speed and therefore very little loss of energy. So we talk about this here. If a neutron collides with an atom of high mass, it will bound off with little loss in kinetic energy due to conservation of momentum. Therefore, the moderator must contain atoms of similar atomic mass to the neutron, so a large amount of energy will be transferred in collisions between the neutron and the moderator. So often they use water, which contains hydrogen atoms, and often they use deuterium, which is water that contains hydrogens with 1 proton and 1 neutron, so that when the neutrons collide with those, they lose energy, gets them back to about this 10 electron volts of energy, and then when they hit one with 10 electron volts of energy, they can cause that induced fission that we talked about on the previous slide. It's important also that the moderator doesn't absorb the neutrons, because if that happened, then they wouldn't be available to continue the chain reaction. So whatever you use as a moderator must not absorb neutrons to form new isotopes, because then they will be lost and not be able to cause the chain reaction. So, if you want to go and make a nuclear bomb, the first thing you need is a moderator. But that's not the only thing that you need. Now, This diagram talks about uranium-236, which will undergo induced fission, but it's not that common. The more common naturally occurring form of isotope is uranium-235 that undergoes fission, but uranium-235 in itself is also not as common as the most common isotope of uranium, which is uranium-238. So if you get some naturally occurring uranium at a place like Roxby Downs where they mine it, it'll contain mostly uranium-238 with a small amount of uranium-235. The 238 does not undergo fission. No fission. Or no induced fission. So if that gets hit with a neutron, all that does is basically absorb the neutron to form a new isotope. So if you've got a large amount of uranium-238, you're not going to make a very good nuclear bomb because it's going to absorb the neutrons and therefore they're not going to be available for the chain reaction. So what you need to do is a process called enrichment. So, as I said, the naturally occurring uranium contains mostly 238 but also some T35. So they enrich that, and that has the effect of increasing the fraction of uranium-235 so that you can get to a point where there's enough uranium-235 there that a neutron is more likely to hit one of those and cause an induced fission and the release of a large amounts of energy rather than be absorbed to form a new isotope. You don't need to really know how they do this, but it's essentially done by using a centrifuge. And basically a massive centrifuge which basically spins, I think they melt it first but I'm not sure, spins the uranium. The heavier isotopes go to the outside, the lighter ones go to the inside, and that then basically means that you can isolate that enriched form of uranium-235 and use that for your nuclear bombs or your nuclear power plant. When they're looking for evidence that places like North Korea and Iran and that so forth are engaging in nuclear technology, they often look for evidence of these massive centrifuges used to enrich uranium because that's a sign that they are pursuing a nuclear program. Now, the other thing that's important here in terms of not so much a nuclear bomb but our nuclear power plant is that not all of the neutrons are emitted immediately. Some of them are released with a slight delay, and this is really important, for example, in a nuclear power plant, of allowing you to be able to control that reaction. So if you can control that reaction, then you can sort of contain it and use it to make nuclear power. Now, as I said previously on the last slide, there's no unique fission for any given nucleus, so you can get many possible products of fission. So if you look here, this one goes to barium and krypton, this one goes to cesium and rubidium, this one goes to strontium and xenon, and so on. And also importantly, all of these products of nuclear fission themselves are likely to be radioactive. Why is this the case? This is because the stable neutron to proton ratio increases with increasing atomic number. Think back to the structure of the nucleus topic and look back at that graph if you're not sure. When an atom of high atomic number splits into two, the products have a lower atomic number and do not require so many neutrons to be stable. Remember that neutron to proton ratio increases as you increase in atomic number. So when you sort of split them in two, both things don't need the same ratio, they need a smaller ratio. So if they've got the same ratio, they have an excess of neutrons. If they have an excess of neutrons, they will therefore undergo beta minus decay, where a neutron is converted to a proton. So now, hopefully you know everything you need to know about going and making a nuclear bomb.